50,000 years ago, water was disappearing from the heart of Australia. Clay cracked across the bottom of a shallow lake, while creatures found nowhere in the modern world gathered around its last dark pool. Diprotodons, as heavy as rhinoceroses, slowly trampled the shoreline. 2-meter-tall thunderbirds remained close to the vegetation. A marsupial lion could be hiding in the dry grass, while a giant monitor lizard moved silently between the rocks. But during that season, another hunter appeared beside the water. It was smaller, physically weaker, and possessed neither powerful jaws nor protective armor. Yet it could cooperate, preserve fire, and return to places where animals would inevitably gather again. Soon, most of Australia's giants would vanish. The main question is not which threat delivered the final blow. The deeper mystery is why several dangers converged in the same place at almost the same time. To find the answer, we must follow the fate of this waterhole, from the first human footprints to the final bone buried in its dried mud. Australia at that time was not an endless desert. Forests, open woodlands, grasslands, and chains of lakes formed a shifting mosaic shaped by rainfall. Diprotodons wandered across this landscape. They were the largest marsupial herbivores ever known and weighed several tons. Giant kangaroos, massive short-faced browsers, and enormous flightless birds lived beside them. Predators followed their movements. The marsupial lion was not a true lion. It was a distant relative of wombats and koalas, whose incisors and molars had evolved into powerful cutting blades. The giant monitor lizard appeared even more intimidating. It was related to the modern Komodo dragon, but grew considerably larger. This ecosystem survived not despite drought, but alongside it. Australia's climate had fluctuated for thousands of years. Waterholes shrank and returned, while vegetation retreated and later reclaimed the plains. The giants had survived earlier dry periods. Climate deterioration alone therefore cannot explain everything. This time, the familiar cycle encountered a completely new force: humans. Evidence from northern Australia suggests that people may have reached the continent around 65,000 years ago, although the precise timing remains debated. At the last waterhole, the advantages of being enormous became dangerous weaknesses. A large body required more food and water. Slow reproduction meant that the loss of an adult female or a generation of young could not be quickly replaced. Humans did not need to slaughter entire herds. They only had to take young animals regularly, drive prey away from the shoreline, or return to the same location during severe dry seasons. But there is a problem with the hunting hypothesis. Australia contains very few unquestionable sites filled with Diprotodon bones, bearing signs of large-scale butchery. The image of a continent-wide massacre is poorly supported. Does that mean humans played no role? No. Hunting may have been rare, scattered, and almost invisible in the archaeological record. For species that reproduced slowly, even limited additional pressure could become disastrous, especially when their numbers were already falling because of water shortages. Scientific models and fossil dates do not always agree, yet many studies place the decline of the megafauna after humans began spreading across the continent, rather than linking it to one sudden climatic event. Regional evidence also suggests a more complicated process in which access to fresh water and human activity worked together. The clearest evidence was preserved not on a bone, but inside fragments of eggshell. Across Australia's dry interior, archaeologists have found pieces of enormous eggs darkened on only one side. This pattern of heating is difficult to explain through a natural wildfire. It is more consistent with an egg placed beside hot coals, opened and then discarded into a fire. Analysis of ancient proteins confirmed that some of these fragments belonged to Genyornis, a heavy, flightless bird standing more than 2 meters tall. Humans were collecting and cooking its eggs at roughly the same time the species began to disappear. This does not prove that every Genyornis was killed by people, but for a bird that produced only a small number of large eggs, repeated nest raiding struck at its most vulnerable point, the next generation. An adult bird could defend itself beside the water. An egg could not. Here, exploitation becomes almost invisible. There are no spear points embedded in ribs and no fields covered with carcasses. There are only a few empty nests during each breeding season. Over a single year, that may seem insignificant. Repeated across centuries, it could destroy a population already losing feeding grounds and reliable water. Humans brought more than spears. They also brought controlled fire. Wildfires had existed in Australia long before people arrived, and many plants were adapted to them. But the frequency, timing, and location of burning may have changed. Small fires could clear pathways, improve hunting conditions, and encourage fresh plant growth. On a local scale, they may even have created valuable feeding areas. Yet when fires returned too frequently, or burned during exceptionally dry years, the ecological mosaic began to simplify. Dense patches of vegetation that retained moisture for longer periods disappeared. Plants eaten by large herbivores became less common. Then, a strange feedback process may have begun. As the giant grazers and browsers declined, fewer animals remained to consume and trample the vegetation. More dry plant material accumulated, allowing later fires to burn with greater intensity. For this reason, charcoal preserved in ancient sediments cannot be treated as a simple confession of human responsibility. Increasing fire may have contributed to the crisis, but it may also have been one of its consequences. Studies of pollen, microscopic charcoal, and fungal spores associated with animal dung suggest that megafaunal decline, vegetation change, and altered fire patterns occurred close together. However, the exact order differed from one region to another. Now the drought deepens. The shoreline retreats by several meters, and the remaining water becomes warm and muddy. Diprotodons arrive earlier because distant water sources have already vanished. Thunderbirds search for soft vegetation along the water's edge, but less of it survives each season. Predators wait in the shade, while human hunters watch from higher ground. In a system like this, climate does not need to kill animals directly. It only has to force every participant into the same shrinking space. The fewer waterholes remain, the more predictable the movements of prey become. The poorer the vegetation grows, the more damaging the loss of every adult animal becomes. The fewer nests produce surviving young, the harder recovery becomes after a bad season. Some populations may have disappeared early. Others probably survived longer near permanent sources of water. This is why scientists still debate the exact timing and cause of the extinctions. In some parts of ancient Sahel, evidence connects the later disappearances with declining water availability, vegetation change, and altered fire regimes. Other records suggest that the giants had survived earlier severe climatic fluctuations, while their final decline coincided with human presence. The contradiction fades once we stop searching for a single killer. Climate reduced the space available for survival. Humans added pressure. Fire transformed the landscape on which the struggle took place. The final scene does not need to be violent. The last Diprotodon may simply have failed to reach the next waterhole. The last female Genyornis may have laid her eggs in a nest that hunters had already learned to find. The final Marsupial lion may have followed increasingly scarce prey until its own population fell below the point of recovery. The disappearance of Australia's giants probably did not happen in a single day, and it did not have one face. It was built from repeated losses: another drought, another fire, another successful hunt, another empty nest. Separately, none of these blows appears fatal. Together, they can change the future of an entire continent. When the giant herbivores disappeared, vegetation patterns changed. When large prey vanished, specialized predators followed them into extinction. Australia did not become lifeless, but it became a different world, increasingly dominated by smaller, faster, and more adaptable species. The final waterhole is only an image, but the conflict surrounding it was real. Water scarcity, changing fire, and a new intelligent hunter proved more powerful than size and millions of years of adaptation. That is why the question of responsibility remains uncomfortable. Australia's giants were not destroyed by a single enemy. They were lost when several threats converged, and each one made the others more dangerous.